And you're right on time, actually.
Yep. Thank you for your patience. I am Unmesh Sahasrabuddhe. I lead the engineering and product teams at Universal Quantum. I'm not a quantum physicist. My background is in designing complicated hardware, software stacks, especially in the machine learning space and GPU space. So today, I want to talk here. I'm here to talk about what is needed to build computers and the rest of the infrastructure to unleash the full potential of quantum computers and how we go about it. Okay, so before I get to that, let me briefly tell you who we are. We are a 70-people startup headquartered in the United Kingdom. Our founders have come out of the physics department at University of Sussex, and they have been focused on thinking about and researching and designing techniques that are needed to build fault-tolerant computers for over 15 years now. And we also have offices in Germany and the United States. In Germany, in Hamburg, we are building 2 computers for DLR, which is the German Space Agency. So if you look at the space in which quantum computers are likely to come off, are likely to provide the benefits, they are expected to be quite transformative across many sectors of the economy in many, many domains. Whether it be drug discovery, material science, optimization techniques, big data analysis, financial applications, encryption or decryption. But what that needs is they need a few thousand nearly perfect qubits. But if you look at what the state of the hardware is today, or even for the foreseeable future, it is quite far from having nearly perfect qubits. So what is needed here is the quantum error correction techniques, which is what Alexandra from Riverlane, she went into details of. And that quantum error correction technique is what will help us move forward. And what they do is, what those techniques do is they combine several physical qubits into a logical construct where you get the errors, low enough errors that you need to to use those algorithms. So the implication of that is that you need many more qubits to create a logical qubit. So for example, if this approximately 6,000 qubit RSA, Shor's algorithm to decrypt RSA encrypted data is likely to require millions of physical qubits on a trapped ion computer. And but longer term, I think we do believe that those numbers will come down, mainly through research in multiple areas. One is the algorithms themselves, then the quantum error correction techniques, as well as improvements in the hardware error rates. So when you look at what the road to that useful quantum computing is, I think the destination is clear. It's just that the path is not so much. A lot of applications have been scoped out from an algorithmic point of view, but when we pair that with the quantum error correction protocols, what we realize is that potentially a million qubit, a million physical qubit quantum computer will provide the necessary quantum advantage, at least for many of a broad spectrum of these applications. And when you look at the state of the art right now, it is quite there's a wide range of what you see, the number of qubits, the quality of those qubits, but everyone is far away from where we need to be. So we need to be careful that we do not fall into the hype of just the sheer number of qubits without looking at the underlying quality of those qubits. And as the community makes progress on hardware capabilities and other things, broader applications will become available. And it is hard to envision the impact. It is very similar to where classical computing was in the 1950s and 60s, whose pioneers didn't quite envision what effect it would have, and we are still seeing it unfold, the impact of the digital revolution, even as we speak, and there's still long ways to go. So there's a somewhat similar expectation in terms of where quantum computing will provide benefits over the longer term. It's hard to envision. But since these useful computers are like many, many years away, a lot of people in the research community have been focusing on NISQ sized quantum computers, where they are looking into like, okay, what kind of algorithms can be developed to get some use out of these low-range quantum computers. So you could look at like improvements in VQE or quantum approximate optimization algorithms or other items. And but the challenge there is that the theoretical underpinnings of like what is the actual feasible speed up that can be achieved is still like not quite there. On the other hand, when you think about the high-end fault-tolerant regime, the device depth is known. The circuit depth is known, and so like for example, like Shor's algorithm, we do need we do have an understanding of what is the circuit depth that is needed, and we also know it for many of the quantum chemistry simulations. So bottom line, like we just continue to need large-scale computers for compared to like where the state of the art is today. And the industry looks at it in many different ways. Like one of the recent ones is the TerraQuap, which is essentially like an error rate on logical qubits in the regime of like 10 raised to minus 12. And this is definitely known to provide quantum advantage across a broad range of applications. And on the other hand, there's the functional qubit, logical qubits. All that means is that they improve the error rate compared to like what the underlying physical hardware rate is. It's not clear like how much benefit that they are likely to provide. And so I think over time, the reality is that rather than these extremes, people like we're going to find somewhere in between, like in terms of what the logical error rate, what logical error rate we can get to that will continue to provide broad spectrum applications. And as the hardware quality improves, like say like the error rate goes from 10 raised to minus 3 to say like 10 raised to minus 4, we can have a lot more TerraQuap qubits out of the same physical number of qubits. So let's take a little bit of like what we are doing at Universal Quantum to build large-scale quantum computers. The first thing that we are doing is that we are building a vertically integrated microchip using standard fabrication processes. We're really not looking into inventing new ways of doing things. And the second thing that we do differently compared to others in the ion trap community is that we use a handful of global microwave fields, whether you're working on 10 qubits or a few 100,000 qubits, it's the same handful of global microwave fields to perform the gate operations. And we bring the ions in and out of resonance in a magnetic field gradient. The third one is that we have a very shuttling-centric hardware. So what we do is we literally move our physical qubits around the chip. And this is expected to provide like long-range connectivity between various qubits to do logical operations, hopefully with fewer number of physical qubits. And we have, and what we do is like we just start laying these chips next to each other, even with certain gaps between them. And we just simply shuttle it across from one chip to another. So that's how we expect to scale very, very rapidly. Once we have this chip in production with a few modules connected, we can just keep growing that really fast. And what we see is that the speed and fidelity of shuttling across chips is really the same as what we see within a chip. And those are very favorable to the for the logical qubit regime where we need to get to. And so the way we see the world is this is really a close collaboration between end users and high power compute and classical compute. And we are making it accessible over cloud. I have no idea if my screen went away or. Okay. Okay. So the call to action here really is that we need to work very closely with the not only like the hardware manufacturers or like the people who provide software access to the hardware, but it is also working very closely with quantum error correction partners like Riverlane, or like the algorithm developers, like University of Copenhagen is pursuing some of those things. There are a lot of other research areas going on. And combine that with classical, like how do you take a classical workload? How do you split it between classical compute versus quantum processors? How do you meld it all together? What do you do on a HPC versus what do you do on a quantum processor? There's a lot for us as a community to work together, and this is our really call to action in terms of like we need to do that. We need to understand how the data flows, how the control flows across all of the entirety of the use case. And that's what I think we are really after in some sense in terms of how we view collaborations and like how we need to work together as part of the Open Compute group or otherwise. And that was my last slide. Thank you.